All right, let's dive right in. Today, we're talking about the absolute bedrock of transport demand modeling. We're going to pull back the curtain and look at the digital DNA that lets planners, predict the future of how our cities move. I mean, think about it. It's a massive question, right? You're about to pour millions, sometimes billions, of dollars into a huge infrastructure project. You have to know it's going to work. Well, the answer lies in building a kind of digital twin of our transport world, and that's exactly what we're going to explore. So here's our game plan. We'll kick things off with a why. Then we'll walk through the classic 4-step process. After that, we'll get into the real meat of it, defining zones and building networks, the core geography of any model. We'll wrap up by seeing how it all connects and why getting this foundation right is just everything. Okay, so first up, why even bother with all this? Why build these incredibly complex digital models in the first place? Well, it all comes down to making smarter decisions when the stakes are incredibly high. You can think of these models as our virtual laboratories. They're sandboxes where we can play what if? What if we add a new toll? What if we build a dedicated bus lane? What happens with a new high-speed rail line? We get to see all the ripple effects on the economy, the environment, on society as a whole before a single cent is spent. It's how we turn a cool idea into a solid, evidence-based plan. All right, let's talk about the framework that has really been the backbone of transport planning for decades. Understanding this process is key to seeing where our main topics today, zones and networks, really fit into the puzzle. This is the classic, the industry standard blueprint. Step 1, trip generation, asks, okay, how many trips are we even talking about? Then trip distribution figures out where they're all going. Step 3, mode choice, predicts how people travel. Are they taking a car, the bus, maybe a bike? And finally, trip assignment puts those cars and buses onto the actual roads. But here's the kicker. None of this, not a single step, can happen without the two things we're focusing on today. The zones where the trips start and the networks they travel on. They are the stage for the whole show. Right, so this is where it gets really interesting. Before we can model a single trip, we have to translate the real, physical city into a language a computer can actually work with. And that process starts with the humble zone. So what is a transport zone? Well, it's the basic building block of our model's geography. Think of it like a digital neighborhood or a specific district. And the golden rule here is what we call homogeneity. You really want a zone to be mostly one thing. All residential, all commercial, all industrial. Why? Because it makes it so much easier to predict the number and type of trips that are going to start or end there. Now, drawing these zones on a map isn't random. It's a mix of art and science. There are some hard rules. For instance, you don't draw a zone that crosses a river or a freeway, because those are natural barriers to travel. You try to line them up with things like census tracts, because that's where we get all our precious population and employment data. Big, unique places like an airport or a university, they usually get to be their own special zone. But it's always a balancing act between getting super detailed and actually having the data to back it up. Okay, so we have these zones, these sort of abstract polygons. How do they actually plug into the street network? Through these two clever ideas. First, the centroid. You can think of it as the zone's center of gravity, just one single point that represents all the trip-making activity inside it. Then, the centroid connector is like a virtual on-ramp, a special link that takes all those trips from the centroid and loads them onto the real road network. So we've got our zones. Now we need the pathways to connect them all. This is where we build the network, the digital skeleton that the entire transport system hangs on. This digital skeleton might look incredibly complicated from the outside, but here's the really cool part. At its core, any transport system, I don't care if it's a simple local street grid or a massive regional plan with trains and buses, it can all be broken down into just two simple, powerful parts: links and nodes. And it really is that elegant. A link? That's just a stretch of road between two intersections, or a part of a bus route between two stops. A node? That's just the point where those links meet. An intersection, a train station, you get the idea. That's it. An entire city's complex web of movement, all boiled down to a collection of links and nodes. This is where the magic really happens, where the model starts to feel like the real world. Each link isn't just a line, it's packed with data. We tell the model its distance, its free flow speed, its capacity, but the most important piece of information, the real secret sauce, is the volume delay function. This is a little mathematical formula that tells the model exactly how travel time gets worse as more and more cars try to cram onto that link. It's literally the engine that simulates traffic congestion. So we've got our zones, which are generating trips, and we've got our network of links and nodes ready to carry them.
Now it's time to put it all together in the trip assignment step. This is the moment of truth. The model takes all those trips going from one zone to another and starts assigning them to the network, always looking for the cheapest path. And in this world, cost usually means time. But here's the cool part. As the model loads cars onto a link, that link gets slower because of the volume delay function. So its cost goes up. The model sees this, and in the next go-round, it reroutes some traffic to other, now cheaper routes, until everything settles into a stable balance, or an equilibrium. It's basically simulating how all of us as drivers collectively try to find the best route to work every morning.
And it's really important to see that the logic for choosing a path is totally different depending on the mode. For highways, it's pretty straightforward. People are trying to minimize their travel time, which is affected by congestion. But for public transport, oh man, the cost is so much more complicated. It's a mix of how long you're on the bus, how long you have to wait for it, how many times you have to transfer. All of that gets factored in. A route that's actually longer might be cheaper if it means less waiting around at a bus stop. Okay, let's bring this all home and talk about why these foundational pieces, the zones and the network, are so ridiculously important to this whole endeavor. This quote really says it all, doesn't it? These models aren't just for academic papers, they are the fundamental tool we use to make decisions on massive transport projects. They're what gives us a structured way to test our biggest ideas about the future of our cities. And here is the bottom line, the one thing you should take away from all this. If your basic geography is wrong, everything else you build on top of it will be wrong too. A sloppy zoning system, a network that gets capacity wrong, that's the classic garbage in, garbage out problem. And the result isn't just a bad forecast, it's the very real risk of making a terrible multi-billion-dollar decision based on that bad forecast. So that leaves us with a really fascinating question to think about. For decades, we've built these zones and networks using static data from surveys and the census. But today, we're swimming in a sea of real-time data from GPS, from our phones, from transit cards. So the question is, how will this constant flow of dynamic data change the way we define these fundamental building blocks in the future? Could they become more fluid, more personalized? That's the challenge and the incredible opportunity that lies ahead.